Thanks, Anne Marie. And now I think it's about time. We'll start with the introductory video for our first laboratory, and then you'll hear directly from Jefferson Lab after we finish this introduction.
How do we explore the nature of matter? There's an entire subatomic world that lies within the nucleus of an atom. Protons and neutrons, quarks inside protons and neutrons, and the mysterious strong force that binds them all together. Every year, nearly 1,700 scientists from around the globe flock to the U.S. Department of Energy's renowned Thomas Jefferson National Accelerator Facility in Newport News, Virginia, to explore that world. It's research that can't be done anywhere else. Because subatomic particles are incredibly small, scientists need an incredibly big microscope to study them, like Jefferson Lab's CBAF. The CBAF, or Continuous Electron Beam Accelerator Facility, is the world's first large-scale superconducting radio frequency particle accelerator. It uses electrons to probe the atomic nucleus. CBAF is essentially built on a racetrack 25 feet underground and nearly a mile long to accelerate beams of electrons to nearly the speed of light before they collide with atomic nuclei to reveal matter's secrets. But Jefferson Lab's expertise goes beyond nuclear physics. It's also at the global forefront of designing and building particle accelerators. It's a world leader in cryogenic technologies to keep experimental devices colder than the far reaches of space. It's improving particle detection for ever-demanding nuclear physics experiments, with life-saving applications in nuclear medicine like cancer detection and treatment. It's pushing the boundaries of computing, amassing hundreds of thousands of gigabytes of research data every day, and harnessing the might of supercomputers and artificial intelligence. Finally, Jefferson Lab also looks to the future. Its STEM programs reach thousands of students and teachers every year, and it accounts for more than a third of all doctorates in nuclear physics in the U.S. Every day, Jefferson Lab leads the way in exploring the nature of matter. For you, for us, for our future.
Good morning. My name is Steve Gagnon, and I'm joined today by Lisa Searles-Law. Especially good morning to you if you're watching from the West Coast, since it's pretty early out there right now. As you may be able to assume from that video that just showed, we both work at Jefferson Lab. We're members of the Science Education Group, and it's our job to do outreach with students. At the lab, again, we study inside the nucleus of the atom, and we do that with our accelerator that takes electrons, speeds them up to roughly the speed of light, and then it smacks them into the nuclei that we want to study. So we like to equate this to a microscope, right? We're trying to look inside the atom, but it's not like a traditional microscope. There's no eyepiece that the scientists go to and put their eye on and say, oh, hey, look inside the nucleus there. But it's a good model. It's a good model to have inside your head, that it behaves kind of like a microscope. And the general purpose of a microscope is to take something that's small and close and make it look large. Now, you might be able to tell from where I am, I'm not at Jefferson Lab right now. I'm actually in my backyard in an observatory that I built, and what's behind me is not an accelerator, right? That's a telescope back there. And like microscopes take small things that are close and make them large, the purpose of a telescope is to take something that's large but appears small because it's far away and magnify it. There are two main jobs that a telescope needs to do in order to do this right. First is to magnify, right? You want to be able to take that object that's large, that seems small, and make it larger, make it appear larger, so that you can see the details that are in it. The other thing it needs to do is to gather light. Now, our eyes, the way we get light into our eyes is through our pupil. And they're only but so large, right? Your eye is only so big. It would be really nice if at night, if your pupil could be like the size of your face, right? Because then you could get a lot of light into your eye. But if that happened, I mean, first it would freak people out, right? Because you're walking around with this pupil size, this plate-sized pupil on your face, and where would your nose go? And the whole redesign of your face would be a big issue. But that's basically what the telescope does for us, right? It's able to collect a lot of light and bend it down so it can go into our pupil. And of the two, between magnification and gathering light, magnification is sort of the flashy thing, right? It's the nice thing to put on a box if you're trying to sell a telescope, right? It's nice to say, this has 600 power. And you look at the one beside it, this one has 800 power. And it's like, oh, this one has like 200 more power than this one. Marketing numbers, right? You normally don't want a telescope that magnifies 800 times anyway. It doesn't, the optics don't really work that well with that. What's more important though is the light gathering ability. So the larger the telescope is, the better it can gather light. Um, there are two general types of telescopes. You have things called reflectors, and those use mirrors in order to shape the light. And another type is called a refractor, and that uses glass lenses, kind of like would have a magnifying glass. And again, they both do the same job. It's to take the light and bend it so it goes into your eye. And you can have mixes also. They're telescopes that use both lenses and mirrors. What's behind me right now is a refractor. The front of it is a lens that's 127 millimeters in diameter, so 5 inches. So again, it's like having a 5-inch pupil on your face instead of your regular eye. Um, One generally overlooked component of the telescope is the mount. And the job of the mount, uh, it's to move the telescope so you can point it where you want to point it, and it's to not move. And you might be saying, wait a second, these are two contradictory things, right? You want it to move and you want it to not move. Well, when you want to move, right, you need to be able to point it in the sky. And it's nice if you can track also. Since the Earth rotates, if your telescope is staying put, but it's attached to the Earth and it's rotating, the things you're looking at would then drift through the eyepiece and you would eventually lose them. So it's nice if the telescope can track. So you want it to move, but you want it to move in the right way. What you don't want it to do is wibble and wobble and sway in the breeze, especially if you're magnifying stuff, right? If you're using something at, magnifying something 100 times and the telescope wiggles a little bit, well, that wiggle is going to get magnified 100 times also. So a really good mount is one that you don't notice, right? If your telescope is staying put and you're looking through the eyepiece and it's like, hooray, my object is there and it's not drifting away and it's not wibbling and wobbling, you tend to forget about the mount, which is which is usually a good thing. If you're worried about wobbling, then your mount's not so good. But it's usually an overlooked part of the telescope. It's almost as important as the telescope itself. So how do you find things with a telescope? Well, if you go back and think about microscopes again, right? Microscopes, it's basically two-dimensional, right? You have a slide, you put some stuff on the slide, you put the cover slip on the slide, that thing gets smushed. I mean, it's not really two-dimensional, but it's effectively two-dimensional. And when you have your slide, you can move it forward and backward, and you can move it left and right. You tend not to move the slide up and down to find things, right? You need to do that to focus, but to locate objects, you're usually just back and forth and left and right. So really just two-dimensional. Um, Same sort of thing with the sky. The sky is basically two-dimensional, but it's not because you've taken an object and you squished it. It's kind of bizarre. It actually appears two-dimensional because that third dimension is so big, right? You see things in 3D because you have two eyes, and each eye sees the object from a slightly different angle. And if the object is close, right, it's a sharper angle. If the object is far, it's more parallel. Things that we look at in the sky are all so far away. Even the moon, which is relatively close, this little baseline between your eyes, this 5 inches or whatever this is, it's not enough, right? Both eyes basically say, yep, we're looking in the same direction, same thing, sounds legit, it's all good. So that third dimension being so big, you can't tell. If you go out into the night sky and you look up, you can't tell which stars are further than other stars, right? They all look the same distance. And you can't even go by the brightness, right? You could have a intrinsically dimmer star that's close, and then it can appear brighter than an intrinsically brighter star that's further away. So you can't tell by brightness, you can't tell just by looking. Right? It all appears in two dimensions. And unlike a microscope where you are searching back and forth and left and right, a telescope, it's how far around and how far up. How much up do I go and how much do I spin? It's the altitude is how high up and which way do I spin? That's called the azimuth. And right now, I hear someone saying, "But wait, your mount is tilted, right? It's not going spinning like this and going up and down." And somebody way in the back is going, "Yes, it appears to be tilted about 37 degrees." And good, right? This one axis that this thing rotates on is actually tilted about 37 degrees because my latitude is roughly 37 degrees. The point of this is to point this one axis north. And if I tilt it the right amount, it's now parallel with the Earth's axis. And when things move across the sky as the Earth rotates, the mount can track it just moving in one direction, right? One motor can run and it can track things across the sky. They do have telescopes that are, outast. They do spin and they do this, but when they track, you have to do it in two directions, right? You have to move a little bit to the right and then up, a little bit to the right, then up, right up, right up. And then when you're coming back down, you're moving right down, right down. So it's a little bit more complicated with the math. The larger telescopes, the really big ones, the ones you put on mountaintops, they tend to make them with that kind of mount because it's cheaper to build than a big one of these things. And it's actually more structurally sound to do that. The telescope's not going off in weird directions. Problem that they have, though, if you're looking through the eyepiece, uh, the thing you would see would slowly spin. Not a big deal with your eye, but if you have a camera attached to that, it's going to trail in a circle. So what they do is they de-spin with the camera. So as the telescope is moving, the camera is actually counter-rotating to get that all done and good. Great. So what we're going to try to do is look at the sun. So we need to tell the telescope that we're going to do that. So the first thing we actually need to do, we have a little handheld computer that runs the telescope. And this little handheld computer contains within it a model of the universe. And it's not a perfect model, right? It doesn't have every single object in the universe in its memory. And there are new discoveries made all the time, too, right? A comet may appear tomorrow, and this thing may not know about it, and that's fine. In general, models are helpful for understanding. There's a saying that all models are wrong, some models are useful. And what's in here is a very useful model for telling the telescope what's in the sky and what direction this is. So the first thing we need to do is tell this telescope where it is on the Earth. And then we need to tell it when it is on the Earth. And we need to tell it that we haven't moved it since we last turned it off. So now it knows where it is, when it is, and where it's pointing. So it can make a little model and it says, okay, I'm pointing in this direction. And if I want to look at a thing over here, I need to go this much this way and this much that way. And then I should be pointing at it. So again, we are going to look at the sun. And again, I hear somebody saying, but wait, you just got through telling us that this thing is like having a pupil the size of my face. And in addition to freaking people out if I'm walking around like that, I've been told, don't look at the sun, right? My little normal size human pupil is going to burn my eye. And if this face size pupil is pointing at the sun, certainly that's worse, right? This is a bad thing. Good. You're right. You don't want to do that. If you remember, there was a total solar eclipse back in 2017. And at that time, there were a lot of these things going around, right? These are glasses with little filters on them. And you'll notice that they're shiny. And what they do is they reflect most of the light away. It's roughly a factor of a million. So a million photons come in, one of them gets through, the rest of them bounce off. So you can put this on your face and you look at the sun and you don't fry your eye. Well, they make similar ones for the telescope. So here's one for a different telescope, but again, same sort of thing, shiny, so the light bounces off. Even though we're not putting our eye on the end of that, there is a camera back there, and I would rather not set it on fire by pointing it at the sun. Um, Good. So now we should be ready to tell it to go forth and look at the sun. So I will tell it that I want you to look at a solar system object. I want to look at the sun, and please go to it. And even this thing says, wait a minute, buddy. Are you really sure you want to do this? Because you could fry your eye if you look at it. And, don't blame us if you're telling us to look at the sun. Don't blame us if you mess this up. So I'm saying, yes, I'm sure, let's do it. And then the telescope will leap to life. It will point itself in the direction of the sun. And now I need to be a little bit awkward. I need to go over here. I need to adjust this. I need to turn this, that. I need to do this with this. And then hopefully my computer picks up that the camera is there. And it does. And then I come over here and I need to change my camera setting to the telescope. And then I also need to open the rest of the dome. Ta-da! And hopefully we are looking there. Yay. So here's the sun. And your first impression may be, oh, sorry, there we go. Okay, round, which is good. It's actually, I read somewhere it's the most spherical object in the solar system. Basically a big ball of gas, really plasma. But since it doesn't rotate very quickly, it tends to hold a really, really round shape. And you have no idea how lucky we got with this. First of all, well, there are actually some clouds coming in, so we might lose this in a little bit. But it was a little bit cloudy this morning. Astronomy is one of these fun things, right? You have things that are highly predictable, right? You know when the sun is going to rise. You know what the phase of the moon is going to be. And then there are things that you can't control, right? There could be a supernova going off that you didn't know about. There could be a comet appearing tomorrow. So you can predict eclipses like centuries in advance, right? I can tell you where to stand, what time to stand, how long it's going to last. I can't tell you what it's going to look like. Like if it's a total solar eclipse, I can't tell you what the corona is going to look like. And I can't tell you if you'll actually be able to see it because it might be cloudy that day. Who knows? But when we looked at this a few days ago, the sun's face was almost completely blank. But the people who get paid to look at this kind of thing, they were saying, oh, there's a sunspot group that's about to rotate into position because we're seeing a bunch of activity that's coming over the limb of the sun, right? They could see the prominences coming up. And there's also a field called helioseismology. It's basically earthquakes, but on the sun. So they're watching the sun's surface shake. And they said, oh, yes, it's shaking a lot. Something's coming around. So a couple days ago, this big old sunspot group rotated into position. So we actually have something to look at today. I'm going to do my best to zoom in on that. So here's a little group of sunspots. What these are areas on the sun that appear dark, and they appear dark because they are cooler than the rest of the sun. It's where the sun's magnetic field is kind of twisted up, and the bright part of the sun that we're looking at, that's called the photosphere, and it is convective. So think of a pot of boiling water, and the water is like roiling in the pot. It's coming to the surface, going back under, coming to the surface, going back under. The surface of the sun actually looks like that sort of thing. And what happens with the sunspots, the magnetic field, excuse me, suppresses that convection and it gets cooler and it appears darker. So even though these look fairly dark, in reality, if you could somehow pluck a sunspot off the sun and plop it into the night sky, it would be something like 10 times brighter than the full moon. It's only dark by comparison, right? The rest of the surface is far, far brighter than the sunspots. It's kind of like if you have you're using an overhead and you're projecting, text onto the white screen. Well, you can ask people what color is that, they're going to say black. It's like, well, not really, right? It's the projector's not projecting black onto the screen. It's just an area of the white screen that's not getting as much light, so it looks black. Um, you'll also notice it is sort of wavering a bit, and that's not the fault of my mount. My mount is actually fairly capable. What that is, that's the Earth's atmosphere doing that. Happily, this is early in the day. Again, much earlier if you're on the West Coast. But still, the atmosphere is warming up. The sun heats the ground. The air gets warm. The air goes up. Again, convection. Right, hot air rises, cold air sinks, and so you get these bubbles of ascending and descending air that come between the telescope and the thing that you're looking at. Stars twinkle, right, for this same reason. So what you're basically seeing is twinkling, but on a scale of a thing that's not just a point. So if this were a much worse day, it would be trying to look at something that's at the bottom of a swimming pool, right? And this is also why you put your big observatories either in space or on a mountaintop, right? So you're trying to get rid of as much atmosphere as you can. Much, much better in space. You don't actually need a telescope. If you want to do a lot of this stuff, it's nice having a telescope. It's nice having a telescope in an observatory in your backyard. But if you were living in an apartment or in the middle of the city, your landlord may not want you putting an observatory on the roof of your building, which is completely understandable. A lot of this is public domain. A lot of the observatories, especially the ones run by NASA. So if you want to do solar stuff, there's an observatory, a satellite called SOHO, SOHO. If you want to Google that, make sure you put SOHO and then telescope after it. There's an area in New York called SOHO, and that tends to pop up more so in the observatory for some reason. But they put imagery up there like daily. So if you want to see what the sun is doing, you can just go to that. You don't need your own telescope in order to do it. It's much more fun to have your own telescope, but you don't need it. If you're also interested in other things, first, if you want to learn more about Jefferson Lab, our web address is www.jlab.org, or you can again search for Jefferson Lab, and that'll pop up as well. If you're interested in astronomy stuff, there are some upcoming events you might be interested in. May 15th, this coming May, so less than a month from now, the next full moon, there'll be a total lunar eclipse that anywhere on the continental U.S. will be able to see. You also have the Perseid meteor shower coming up on August 11th and 12th, but unfortunately it's a full moon on that night, so pretty much won't be able to see anything with that. Looking further into the future, on October 14th, 2023, there's what's called an annular eclipse. That's when the moon covers the sun, but the moon is too far away to cover the sun completely. So the moon looks too small to cover the sun. So you end up with a ring of sunlight called an annulus, which is why this is an annular eclipse. And on April 8th, 2024, so write that one down because it's kind of far in the future, total solar eclipse. Another total solar eclipse will come across the country, kind of like the one in 2017, but it'll be a different path. So that is about what I had to talk about. And in the time that we have remaining, do we have any questions?
Thank you so much, Steve, for letting us have a great look and a safe look at the sun. I have a question for you that uh, we want to know, how big is the sun and is there a way to measure it?
So the sun is, if I recall correctly, about 1.5 million kilometers across. Um, the easiest way to measure it, if you want to call it easy, um, if you can measure how big the sun appears in the sky. So one way you can do that is by making a pinhole camera. You basically take a piece of aluminum, you poke it with a needle, make a little hole, and then you put that in front of a sheet of paper. And you can then project the sun's image onto the sheet of paper. And if you measure how big that is, and you measure the distance between the aluminum foil and the paper, that gives you a similar triangle with the distance between us and the sun and the actual size of the sun. And so that depends on knowing how far away the sun is. So the sun is 150 million kilometers away. And the way we know that is not with a really long tape measure. You can actually measure the distance to other things in the solar system. You can use radar to actually ping Venus is one thing you can do. So you can actually get a distance with that. We know from Kepler's laws, you know the scale of the solar system with Kepler. But that only tells you that, you know, if Earth is 1 unit away from the sun, then Jupiter is 5.2 units away from the sun, but you don't know how big the unit is. Once you get a direct measurement with radar or through parallax, and you can measure the distance of one thing, then everything else that's orbiting the sun is now known also. So we know the sun is about 150 million kilometers away, and then from that you can measure. We actually have a video on YouTube. We have a series called Frostbite Theater. So if you go on to YouTube, you can search for Jefferson Lab on YouTube as well. And we actually have a video that discusses how to do this.
Great. I think we have time for one more question, and it is, how did you build that telescope in your yard, and do your neighbors use it too?
So I did not build the telescope itself. So it's kind of like when you say, I made a cake. And it's like, well, okay, I mean, I bought the flour, I bought the eggs, I bought the chocolate chips. No, I didn't make the eggs, I didn't make the flour. So same thing with the telescope. I bought the telescope, I bought the steel for the mount, I bought the wood for the building, but I cut the wood and I, you know, put it all together. Yeah, how? One piece at a time. That's basically what it boiled down to. So it took a lot looking at what other people did, and the neighbors don't use it so much. The thing is, when you're out here in the middle of the night, happily the neighbors tend to be asleep. It'd be a little freaky if at 2 a.m. someone just walked into the backyard and was like, "Hey, you know, can I use your telescope?" That would, you know, scare me a bit. But for bigger events like the lunar eclipse coming up, if that's at a reasonable time, we may get some folks coming over.
Great. Well, there is one more. What is the most interesting thing you've seen with the sun or in the sky?
While I answer that, I'm going to actually try to point to a different object. This may or may not work, so we'll see what happens. So there goes that. Most interesting thing, and sorry as I walk away from the microphone, I do need to readjust things. And I ruined my backdrop, but that's okay. So the most interesting thing that I've seen, if I open this up, get rid of the filter. Oh, good, it is there. Sorry. So before I answer that, that little blob that you're seeing, that's Venus. This is not the right setup to look at planets. So you need more magnification for this. But that's Venus, and yes, you're looking at it in the daytime. You can see planets in the daytime. You can see stars in the daytime if you know how to point your telescope. And you'll notice it's not round. It's like a gibbous shape, because we actually do get phases, like all the phases with Venus, since it orbits inside of our orbit. You can get crescent Venus, you can get full Venus, and right now we sort of have gibbous Venus. So the most interesting that I've seen, and we can quibble about what seeing means, but Pluto's atmosphere. I actually detected the atmosphere of Pluto with my eye as Pluto passed in front of a star. That's called an occultation. And if Pluto had no atmosphere, the star would just wink out when Pluto moved in front of it, but it didn't. It faded out slowly, and then a few minutes later, it faded back in, and that was the light of the star going through Pluto's atmosphere. Um, Not the most exciting thing to see, but just knowing that it was with my eye, using the telescope with my eye. So was able to see the star dim out. Pluto at the time was too dim for me to see. So the star went from visible to gone and then back again. And let me
Okay,
turn this off so I can see you all again.
great. Well, we really appreciate you bringing us to your backyard so that we could see the sky as we kick off Earth Day from sunrise to sunset. Thank you
Yes,
so much,
really
Steve.
appreciate you all inviting me and giving me the opportunity to talk to you all. Have a good Earth Day and good luck with the rest of the broadcast.